Okay, so hello and welcome everyone to the 10th week of interactive live sessions for the course on computational fluid dynamics for incompressible fluids. This course is being offered by NPTEL. It's being instructed by Professor Amaresh Dalal from the Department of Mechanical Engineering at IIT Guwahati. My name is Debjit. I'm a PhD scholar at IIT Madras and I'm the TA for this course. And like every other week, we shall be solving some problems together. So this was the week when we finally started our discussions on uh, finite volume method, which is by far the most popular method for solving fluid dynamics problems. So this is really the crux of the course, and we have some very simple questions for this week. So starting with question number one, which is asking us what is the main difference between the finite volume method and the finite difference method? Finite volume method and the finite difference method. Finite difference method is what we have been learning so far, and finite volume method is something which we are just getting into. So the four options are option A, the finite volume method discretizes the equation in terms of volumes instead of points. Uh, Option B says the finite volume method uses central difference scheme instead of the forward or backward difference schemes. Option C says the finite volume method only works for one-dimensional problems. And statement D says that there is no difference between the two methods. So we've got one response in favor of option A, that is the finite volume method discretizes the equations in terms of volumes instead of points. So let's take a look at the solution. It is indeed statement A or option A that says that it's in the name basically. The finite volume method discretizes any, given bigger volume like this into smaller volumes. So something like this. If this is a pipe, this is one way in which I can discretize this. I'll have concentric cylinders like this within, and in the axial direction also will be split. And basically, I'm breaking down a bigger volume into smaller volumes. And my idea is that within the smaller volumes as well, the conservation laws of fluid flow will be valid. And if I can do this for small enough, elements or these finite volumes that I've discretized into, then I can get a continuous solution for the flow field. That's the main, philosophy behind the finite volume method. Any questions on this? All right. If not, we will move along. We'll move on to question number two, which is asking us what is the main purpose or what is the purpose of the flux term in the finite volume method? Is it to option A to represent the rate of change of the physical quantity within each control volume? Is it option B to represent the transfer of mass, momentum, energy, or any other physical quantity across the control volume boundaries? Is it option C to represent the boundary conditions applied to the control volume? Or is it option D to represent the source or sink terms in the equation? So basically, if anything is getting generated or getting destroyed, then whether to represent that or not. A and B is the same. Not really. Why do you think they are the same? Option A is represent the rate of change in quantity is transfer. No, not really. So let's say this is your bank account. This is a very crude way of doing this, but this is your income which comes in. And these are your bills and payments that you pay. So if your income is greater than your bills, over time, the money in your savings account will go up, right? So this going up, this is the rate of change. So if that went up, that means there's a positive rate of change, right? And these are the transfers, the things which come in and go out. For a steady state problem, then you can say that these two things, A and B, they might be the same. But for unsteady cases, it's not so. Okay, so we have a response in favor of option A. That is to the purpose of the flux term is to represent the rate of change of the physical quantity within each control volume. Let's take a look at the solution. It's not, it's the uh, transfer of mass, momentum, or energy across the control volume boundaries. Transfer means out in, and that is change. So this is where I guess you have a misconception. So let's come back to this example. So let's say your income is, I don't know, 10K per annum per month, and your expenses are 5K per month. And you start out with a zero bank balance, let's say. So after the first month, you'll have 5K in your bank account, right? Then in the next month, you'll have 10, 15, and so on. And your transfers, the incomes and the bills per unit time, they remain constant. But the physical quantity stored inside, that is increasing with time. So if I, call your bank balance fee, then your do fee do t is basically 5K per month. Whereas these transfers, the fluxes are 10 and 5 and so on. And there could be generations as well. There could be, interest which gets generated within the system, which has not come in from outside or went outside. So does that make it clear that transfer is not the same as rate of change within the thing? Then it is called transfer across one boundary, I think transfer from CV. The transfer across all control volume boundaries, that's the same as transfer within a control volume. I mean, if you include all the boundaries, then that's what the control volume is surrounded by, the control surface, as we call it. That's not really different from each other. But my point was this. So let's say mm, you, so your difference of transfers, that is, I'll call that F, which is the flux term, that is 5,000 per thousand per month. And let's say you have an interest as well, which is, I don't know, 10% per month. So in this case also you'll have some generation. So in the first month you won't get anything, but in this month you'll get plus one. Then again you'll get not plus one, you'll get plus 0.5. Then something like 1.05 in the second month and so on. Yeah. So so your rate of change within this is a bit more than 5,000 per month, whereas your flux was 5,000 per month. This one and this one. The rate of change and transfers are different. And coming back to the main point of the question, which is the flux term, that is the transfer of mass, momentum, energy, or any other physical quantity that we are solving for across the control volume boundaries. So that is this flux term. So it's usually U phi. So in the context of fluid mechanics and not finance, this is your flux term. So you get the convective term and the diffusive term and diffusion term, and that gives you the flux. All right. So moving on to the next question. Which of the following, question number 3 is asking, which of the following is a disadvantage of the finite difference method compared to the finite volume method? Is it option A, that it is computationally expensive? Option B, that it is less accurate? Option C, that it is less flexible in handling complex geometries? Or option D, that it cannot handle time-dependent problems? Which of the following is a disadvantage of the finite difference method compared to the finite volume method? Is it computationally expensive? Is it less accurate? Is it less flexible in handling complex geometries? Or is it option D, that it cannot handle time-dependent problems? So we have a response in favor of option B, that it might be less accurate. Okay, let's take a look at the solution. It is actually option C, that it is not really good at handling complex geometries. So let's say I have a simple rectangle like this, and I split this up into nodes as I do in finite difference method, and I represent all these points in a matrix. You know, everything nicely lined up, and I can have uniform delta x, delta y, or not. I can, have a non-uniform one as well. But anyway, it doesn't matter. So handling this is pretty easy. Now let's say I morph this into something like this, and then my life becomes very difficult if I'm still trying to use finite difference method. Because then, you need to store the x and y values of each node separately and then try to take care of it, and the whole discretization becomes much more difficult. Whereas if I, broke this down into simple, smaller control volumes, which could be assumed to be rectangular as well, because if I go small, then I can do that. So usually, there are different kinds of shapes which are used. So it could be cuboids, it could be tetrahedrons in 3D, and in 2D it could be squares, rectangles, or triangles. Triangles are more commonly used because they offer a bit of flexibility. Let's say if you have a circle like this, any curvature you can think of that way, then you can simply break this down into multiple triangles. Although it's not accurate, it gives you something similar to the curved feature. So if you take many, many points, then it gives you a good approximation of the curved surface. But anyway, so coming back to the main point, now in this uh, finite volume method, then you just need to solve for each control volume. You just need to take care of what comes in, what goes out, what gets generated, and that simply gives you what happens to the physical quantity within that control volume over time. So the bookkeeping and handling becomes much more easier. Yes, but here also we need coordinates. Yes, we need coordinates, but getting the derivatives and all that becomes much more easier. So let's say using a finite difference method, you need to find out what is the dou phi dou x at this point versus in a finite volume method, you're trying to find out what is the dou phi dou x within this control volume across, maybe these two surfaces, all that becomes much more easier. And another added advantage is that in the finite volume method, we sort of use a staggered grid. So we store the flux terms in the surfaces and the scalars in the cell centers. So that also gives you, like, you have two surfaces, you can take a difference between the two and find out the gradients across those two faces. There is still complexities. You still have to do things, but it has some advantages over this finite difference method when it comes to more and more complex geometries. Okay, all right. So let's move along. We'll move on to question number 4, which is asking us which of these terms need a surface integral to be simplified or handled. Is it option A, diffusion and rate of change terms? Is it option B, convection and source terms? Is it option C, convection and diffusion terms? Or is it option D, diffusion and source terms? All right, so we have a quick response in favor of convection and diffusion terms. Let's take a look at the solution. It is indeed correct. So basically, these are what consists of the flux term, which is, sometimes represented by this J vector, which is U vector multiplied by phi plus the diffusion coefficient into gradient of phi. So this is what the convection term is, and this is what the diffusion term is. And in the standard equation of conservation of J, we have something like this. Not of J, of P rather. So then we integrate this whole thing over a control volume, right? Then this term remains intact. Uh, sorry, I missed a row. So there will be this term, we convert it using Gauss divergence theorem. So this is basically divergence of the flux term J. There is a way to simplify this. We use Gauss divergence theorem and convert this into a surface integral. J dot ds, which is, an unit surface within the control surface. So let's say this is the bigger control surface. This is the elemental surface ds, which has a vector pointing outside the control volume. So this simplification needs a surface integral, and that is associated with the convection and the diffusion terms. All right, so let's move along, move on to question number 5, which is asking us which of these terms need a volume integral while modeling steady flows? Is it option A, convection term, option B, diffusion, option C, source term? Pretty simple stuff. We just saw this in the previous slide. So, source term, I'll just go back. So the source term remains over here. So over time, what it means is how much more quantity of phi was generated within a given uh, small control volume. So usually you can think of it this way. Let's say if there's a heat generation problem and there is a heat source, let's say some 5 watt per meter cube, something like this. There is a Q generation like this. Then in the if you're trying to solve for the energy equation, then this will be your SV, and you need to integrate it over each and every control volume that you're solving for, and over a certain period of time as well. So if your time step is delta t, you need to integrate over time as well. So volume integral over space and time integral as well, to get how much of that physical quantity was generated within that period of time within that control volume. That adds on to the conservation of that quantity. So if you're trying to model dou phi dou t, or the rate of change of any physical quantity, the generation can be found out from here. Anyway, simple stuff. We'll keep moving along. Move on to question number 6 now, which is asking us what is the order of accuracy of the equations as a consequence of the mean value approximation. What is the mean value approximation? So let's say if this is a 1D control volume, and this is, let's say, phi p, and these two at the surfaces are p small e and p small w. The mean value approximation simply says that I'll approximate Pp as Pw plus Pe by 2. So what is the order of accuracy as a result of this assumption? Is it option A, first order, option B, second order, option C, third order, or option D, fourth order? So basically this approximation is some order, uh, some order accurate, n. So is that n equal to 1, 2, 3, or 4? Okay, we've got one response in favor of option B, second order. Let's take a look at the solution. It is indeed second order. So this was discussed in the lecture. You can go back. So basically, if you expand each of these terms, this PW and PE in their respective Taylor series, and then come back to find out what PP is. And so yeah, so this is PP's approximation, and the real value of PP is nothing but integration of phi over this whole control volume. So now if you equate these two, let's call them different names. So this I'll call phi p prime. So real phi p equal to phi p prime, if you do, then you'll get some error which is order 2 accurate, right? Okay. And this holds true for a lot of general cases. I mean, for 2D, 3D, as well as unstructured grids and all that. All right. Moving on to question number 7. It's a match the following type of question. The logic is where is each term stored? So we have some terms on the left-hand side, flux terms and source terms, and where are they stored? In the cell centers or cell faces? Sorry. So if this is my cell, then this is cell center 1, and these are the cell faces, which are 2. And there are two options available, A1, B2 and A2, B1. We've got a quick response in favor of option B, A2, B1. So let's take a look at the solution. It is indeed A2, B1. So the flux terms. So this is exactly similar to the staggered grid idea which we learned earlier. So the flux terms are stored at the cell faces. Instead of velocities, we have fluxes, which are again vectors. And source terms, which are similar to scalars, are stored in the cell centers. As well as it's not just source terms which are stored there. The the physical quantity at a given point of time. So let's say phi, if you're solving, you store phi in the cell center as well. All right. If there are no questions, we'll keep moving on. We'll move on to question number 8, which is asking us which type of boundary condition can be most easily handled by the finite volume method. Is it option A, Dirichlet boundary condition, which is saying things like P equal to C, or is it Neumann boundary condition, which is like mentioning the gradients, or a mixed boundary condition where I have both, or the periodic boundary condition where I say, the P at wall 1 is equal to P at wall 2, that sort of a thing. Okay, we've got one response in favor of option A, which was then changed to option D. All right, let's take a look at the solution. It's actually option A, but if I can guess what you're thinking, then periodic boundary condition should also be the same. And yeah, so the thing is, if I have, let's say, a long 1D case like this, I need the phi wall over here. Dirichlet boundary condition simply tells that this is C, my job is done. I keep repeating it, and if C can be a function of time as well, doesn't matter, and I can do that. And in periodic boundary condition also, this will be so if I call this W1 and this one W2, then this can be equal to phi W2 as well, which is again can be potentially a function of time. So in that case, yeah, periodic boundary condition and Dirichlet should give you the same level of difficulty. But whereas the main learning point over here is that Neumann boundary conditions are a bit tricky to handle. So in case of Neumann boundary condition, what we do is, let's say at this point the dou phi dou x is known. Dou phi dou x at the wall is some known quantity. I call that, let's say, C prime t. So there what we do is we introduce something called ghost cells or fictitious cells. Cells which do not really exist. And then I say that, let's call this PG, sorry, call this PG and this one P1. Then I'll say that, okay, then P1 minus PG divided by whatever is the spatial distance between them, that is equal to dou phi dou x at wall, which is given as C prime T. Now this one has to be solved then over time. So you're solving for extra cells which do not really exist, and that adds a bit of difficulty. So that is why Dirichlet and periodic boundary conditions would be more easily handled by the finite volume method. Any questions on this? Okay, and let's move along. Move on to question number 9, which is asking us explicit schemes for solving finite volume method are limited by issues regarding what? So what are the disadvantages of using explicit schemes? Is it option A, accuracy? Is it option B, stability? Is it option C, convergence? Or is it option D, all of the above? This is actually general. I mean, it's not really for finite volume method only. It could be for finite difference methods as well. B, stability. Let's take a look at the solution. It is indeed B stability. So in explicit schemes, your delta t has to be less than a certain threshold, right? So which are dictated by different stability criteria. We learned about the CFL criteria and other things associated with it. So this is the main disadvantage of explicit schemes. It's simple, it's very simple to implement as compared to implicit schemes, but the problem is the you have to pick a good enough time step, a small enough time step, so that you can get a stable solution. Right? Okay. Moving on to the last question after the session, which is asking us that there's a statement at first which says that implicit schemes for solving finite volume method can use large time steps because they are unconditionally stable and they don't suffer from the same issues which explicit schemes do. So it can use large time steps without any stability issue. Then what is the main reason why time step size is kept small in such situations? Is it option A to increase accuracy of solution? Is it option B to ensure stability? Is it option C to capture the physics at small time scales? Or is it option D, none of these? Okay, we have got one response in favor of option A, that to increase the accuracy of solution. Let's take a look at the. So it's actually option C that, your. So let's go through these negative ones one by one. So stability is not the thing. Stability you can use without any issue. Uh, Accuracy of the solution also doesn't really change because once your solution has converged, you get the correct solution at that time step. So let's say at T you got some solution and you take a very large time step and you reach, C plus delta T. Now, this is correct at that increased time as well. So let's say this was time t1 and this was at t2. This is the correct solution at t2. The flow field would have become this thing only at t2. So accuracy isn't really different between, if you had taken small time steps or large time steps. The only thing is, if you uh, take a very large time step, then you miss out whatever is going on in the small time scale. So that's the main reason why time step sizes have to be kept small enough to look at how the solution is evolving with time. Okay. There's something in the chat box, but truncation error increases by large time step. Yeah, but how much? I mean, truncation error is there, that's true, but no, then again, if your solution has converged, then that is the correct solution at time step at time t2, right? Actually, there also error increase. Hmm. Truncation error shouldn't really come in here. Hmm. Okay, I'll think about it, but you could be right that truncation error comes in and that affects the accuracy of the solution. But I think there should be some way to show that truncation error doesn't really matter. It is in one lecture. Okay. In this week's lectures? Okay. Anyway, it makes sense. I agree. So, okay. So that was the last question for today's session. Thank you. If you have any questions, you can go ahead. Yeah, sure.
Uh, just a minute. Yeah. Um, can you please open lecture notes?
Lecture notes. Okay, hold on. Can you see my screen? No, right?
Hmm.
Hold on. Yeah,
Yeah, lecture 2.
one second. I'll start presenting here. Yeah, lecture two.
26. Can you please move? Why? Okay. Can you please move next slide?
Sure.
Yeah, further next. Okay, here.
Hmm.
So, like, till the point when we introduce the dE plus dW, those terms, that's fine. The
Hmm.
second equation.
Yeah.
But once we introduce this AE is equals to DE,
Hmm.
now why this special AE? I don't understand. And one thing,
Hmm.
because already we have taken DE something,
Yeah.
like, and the second thing is we changed that small e to capital E. Why this thing?
Okay. So this is just to maintain consistency with other processes as well. So this one is a diffusion problem, and if I remember correctly, this is steady diffusion, right? Yeah. So this is a steady diffusion problem. So this has only a few terms, and that's why the relation between AE and DE are so obvious that they are just equal to one another. But you can extend this to unsteady diffusion, then unsteady convection diffusion problems as well. Then what is done in practice is this form, this equation, if you can see this one, this AP equal to summation of A N B P N B plus B. This standard form is, cast every time. So any given equation you have, it will be discretized. All these, mathematics will be done. Then finally, we will write the equation in this form and then try to solve it. So this one
Yeah.
may be simple and easy, but let's say the other one only. The In the third lecture, we studied unsteady diffusion, right? Then also with all the after all the dirty math, let's take a look at this one only, explicit scheme. And also we cast the problem into this form where APCP equal to some summation over A and B, phi and B plus something. So
So I can
here,
write DNB. What's the what? How does it make difference?
it doesn't matter. Yeah, it's the same.
Yeah, and
Mm.
why? And capital means I am shifting my attention from small e to capital E. That actually makes a difference because it is delta x by 2 like away from the where we
Mm-hmm.
are taking the
Right.
attention. So why we use that capital E? Or
Yeah,
is
because
it just to say that we are at each direction or something?
no, see, there's a particular reason why. So you see here, right? Phi and B, these are the fees in the neighbors. So those will have a subscript capital E, capital N, and so on. And these A's also we assign to those neighbors. So A would also carry capital E, capital N, the capital
No, but
notation.
yeah, that I understood. But
Mm.
what I am saying that there, the equation I have shown that at that place we are actually at phase. We are
Hmm.
calculating flux. We are at small e, not at capital E. but all of a sudden we change it to capital.
Mm. Mm, this would be best with an example. So let's say, do you have the week 11? Have you seen the week 11 lectures?
No, not right now. Up to
Okay.
10th only.
So you'll see there when we are doing, the convection, diffusion things as well. Not yet vector notes. Volume two. So that thing that giving capital letter notation to the A variables, the only reason is to maintain consistency across all methods. So in these later methods that we will learn, there also finally everything is written in that A neighbor into phi neighbor form. So here also you'll see certain things done. And then this one, this DE minus FE by 2, that is written as A capital E because later on that multiplies with P capital E. You see here in this equation. Sorry, can't really highlight, but you can see if you can see my cursor, this is the equation I'm talking about.
Okay, so what I am understanding that
Hmm.
because we are taking phi at capital E,
Yeah,
just to look similar, we use
exactly.
A, but actually we are at phase while calculating
Yeah,
A.
so the components of the A could be they could come from face or they could come from somewhere else as well. Usually they come from face because it's either convection or diffusion, right? The fluxes.
Okay, okay.
The source term anyway will be an additional term
Yeah,
that won't really contribute to these neighboring variables.
okay. And
Yeah.
the next thing is like
Mm.
it was told,
Where were
I
we?
think in lecture 3
Mm.
or lecture 2, we
Yeah.
that we made in lecture 2. Yeah, here while calculating the flux, it was assumed
Mm.
that it is linear,
Yeah.
right?
Yeah.
So uh, one thing is linear, like I have some temperature,
Mm.
so at east phase,
Mm.
so it is varying linearly across
Uh,
the phase.
across that face, yeah, that's the assumption that in that east face, J varies linearly, or
So I'm
whatever.
just taking an
Mm,
temperature, so
mm,
it is varying linearly.
mm.
And what if it is varying like it is not varying or at, at is it is constant at
Non-linearly, let's say. So the thing is, I will have to take such a small, surface or control volume. This size will be so small that even if it's non-linear, it can be treated as a linear function. So let's say you have a non-linear function like this. Let's say you take a sine wave and you really zoom in and look at a very small distance, then you can simply approximate it as a straight line, right? So that's the idea here, that the whole solution is not really linear. That's not the assumption. The assumption is that since my uh, you know small control volume is small enough, I can assume it to vary linearly.
okay. But to expand this like del phi by del x, we don't need
Hmm.
linearity. Like it is just
No.
an expansion of you Taylor
Hmm.
like Taylor series. So even
Yeah,
if it
yeah,
is non-linear, we can expand it in this way.
yeah, yeah.
Okay. And in the third lecture,
Hmm.
like this assumption I understood, but in third
Hmm.
lecture again there is an assumption. Yeah, it is actually. Can you enlarge it a bit? Just like yeah. The very first term, it was
Hmm.
told like control volume is stationary and non-deformable.
Hmm. Hmm.
That's fine, but like I just need other two term I understood,
Hmm.
but this first term in this,
This one?
like we took, yeah, this one.
Yeah.
Here it is written like
Hmm.
control volume is stationary and
Hmm. Hmm.
non-deformable.
Hmm.
So here we take the differential out of integral
Different,
because I
no, yeah.
made
Thing
this
is,
assumption.
the order of integration is flipped basically. So you do the time integral first. So this was a dodo t of something, and there was a
No, 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 no,
integral over
no,
t outside.
no, no. Just a minute.
Hmm.
Time integral is left. Now here I am only looking at the volume
Yeah,
integral.
yeah.
In this volume integral,
Hmm.
because this is this control volume is a stationary and non-deformable,
Hmm.
we have taken this time differential out of integral.
Integration, yeah.
Means first we are integrating and then differentiating
Hmm.
with respect to time,
Yeah,
instead of first differentiating with respect to time and then taking integral.
yeah.
How does that, like, how I can physically visualize it, or like why this assumption is necessary to make this thing that
Uh, okay. The thing
you
is,
like I just like
yeah.
just a minute, one
Hmm.
extra line, like even if it is deforming or something is unstable,
Hmm.
how does it make a difference? Because I can take the differential with respect to time, I capture the train change and then take the volume integral.
Got it. So let me
Yeah.
share my different screen now. I have to draw certain things to talk about this.
Okay, okay, please.
Um, can you see my screen?
Yeah.
So, okay, first of all, let's discuss the problem. So let's say if your control volume was deforming, or the main idea behind deforming is that that this control volume remains stationary with time. It does not change with time. So let's say after some time it changed into something else. It became bigger or something. So then the problem is whatever, rho phi you had within this and rho phi you had within this, if there was, let's say, no flux, your J was zero, no source term, this was zero. Then also this rho phi would have some change with time. Then also your dou dot T of rho phi would be not equal to zero simply because your control volume changed. Let's say this was your earlier control volume, CV1, and after some time delta t, it became CV2, this bigger control volume. So that's the problem uh, where you cannot really do this. So wait a second. So what was that term?
Actually, we have
The-
integral outside also.
yeah.
Like this, what term you have written? Yeah, dv also.
This is the term that we were talking about, right? So there's a time integral outside also. Let's not talk about that for now. We will just focus on this. So if your CV was not changing, then you can flip this integral and differential. You can take TDT first and put your integral inside. If your control volume was not changing, then these two things are equal. But if your control volume is changing with time, then these two are not equal. You cannot make this jump. This is not allowed.
That's what I want to understand. How?
Yeah.
Why?
Yeah, that was the thing. No? So if your these things are zero, the flux and SP and everything else, then this should have been zero as per your equation. So as per the conservation equation.
No, just a minute. I
Hmm.
am not worried about those flux and source time right now. I'm just looking at the p term.
So
Okay,
let's say if
right?
these two, wait. So let's say if these two were zero, then this would have been zero as well. That's what my whole, uh, you know, algorithm should tell me. But if
Hmm.
the control volume is changing with time, then this is not zero. You can see from, physically, if your control volume expands, it takes more mass into it, and
Yeah.
as a result, more phi into it as well. So your algorithm gives you a wrong answer because because the control volume is not stationary with time. So that assumption is necessary to make this jump. Now, why do we make this jump? For some mathematical reasons. We can go back to the lecture slides for
No, no,
that.
no. Wait here. Wait here. Wait here. Wait
Yeah.
here. Actually, I am. I understand this point that
Mm.
if j and s5 is zero, then it should have be zero.
Mm.
But I cannot interrelate this thing and this flipping of integral and differential.
Okay. So, no, the flipping is why do we flip is different. But can we here the question is when can we flip and when we cannot? We can flip if the control volume is stationary with time, and here with this this cartoon of drawing a different control volume, all I'm trying to say is that if it grows with time, then I cannot do the flip.
Yeah, but why?
Hmm?
Why?
Yeah, this is the reason because this whole argument breaks down then that Dofi Doti, which should have been zero, is not being zero. There is a way to
Okay,
handle
just a
these.
minute. Just a minute.
Yeah.
Yeah, can let's go by some other logic.
Hmm.
Let's say phi just this row phi may be some function f,
Hmm.
right? At
Okay.
every location we have some f.
Hmm.
Integrating this function over the control volume means like adding all the small f on the
Eh,
control
Yeah.
complete whole,
Yeah.
right?
Yeah.
And then taking its differential with respect to time. This is
Hmm.
one thing.
Hmm.
On the other hand, what I do is I
Hmm.
first add up all the f1, f2, f3, let's say if it
Hmm.
is f across the control volume,
Yeah.
and then take the differential with respect to time.
Yeah.
Now, for to make this change, it was
Hmm.
told that it must be like it should not be differential. Otherwise, yeah, I understand. Because if control volume change,
Hmm.
that then itself like it will have we can have different. Uh,
See, this thing only becomes a function of time then. What you're integrating against, that itself becomes a function of time, the control volume.
yeah, yeah. That's what
So,
I understand. Because
yeah,
even if I say if this bigger control volume, then summation of all those f changes.
yeah. So let's forget about integration. Let's take sums now. Okay. So let's say this is F1 at s- time t. After some time t, it became F1 prime t plus at t plus delta t. Or simply I'll just call this T2. Okay. If you are okay with it. And I have another one, F2, which was F2 at T1, and it becomes F2 prime at T2. Then, let's say if we are trying to do something like this, where where I'll do the differentiation first. So that will be F1 prime minus F1 by delta t, and I'll integrate this over the control volume. So integrating, I'm replacing by taking summation, right? So I'll then say this will be F2 prime plus F2 divided by delta t. This is my 2. Sorry, this is my 1. This first method, differentiating first and then integrating. And
Yeah.
the other one, let's call this method 2. So what would 2 give me? 2 would give me the same thing if the CV doesn't change. So 2 would be integration first, so summation first. So okay, so differentiation of this. So let's say the sum of F1 and F2 at time t2 minus the summation of them at t1 divided by delta t. And what was the sum at t2? It was f1 prime plus f2 prime minus f1 plus f2, right? This is the second method where I'm integrating first or taking sum first and then taking the difference over time. So right now, these two are the same, 1 and 2, right?
Yeah.
Now, this was true because this distance was not changing. Now, if I have a moving control volume, you know, a control volume that changes with time, then at T1, these two would be the points of F1 and F2. And let's say I keep F1 same. This this point has now shifted, right? So this is not really F2. And then if you try to calculate this 1 and 2, then they won't be equal.
Yes.
Does it make it clear? Yeah.
Yeah. Actually, yeah, I understood
Yeah.
because by that example that you have taken, that
Hmm.
of changing the control volume itself explain the idea behind everything. Yeah.
Yeah.
So, yeah. So my next
Let's
doubt is
let's
like,
go back to
yeah,
our
we have like in lecture three.
hold on a second. Why is this thing not coming? Okay, I'll share my entire screen. Can you see the lecture notes?
Yeah,
Okay.
in lecture three.
Lecture 3.
Right.
Should I go to the next slide?
Yeah, here F, this F, we are giving weightage to like
Hmm.
uh, n time
Yeah,
level and n plus time level data.
yeah.
But my question is like how we calculate this F?
How we?
Calculate this F.
F is up to you. F is something that you decide. So F being 0 would mean and you're using an explicit scheme. F equal to 1 would mean a totally implicit scheme where you give the weightage entirely to n or n plus 1. And you can do a Crank-Nicholson with, half as well. So F is something that's up to you to decide.
Okay, so there is no like experimental thing or something like based
No,
on
no,
which
no.
I can decide.
No, no. What scheme are you using? That's your choice.
Okay, and like there is only three choices which are told zero, one, and half.
It
Can
could
I
be,
make any other choice?
yeah, yeah. So we learned this in that beta method, right? So
Yeah.
if ft or beta is between 0 and half, then it is conditionally stable, and if it is greater than half to 1, then it is unconditionally stable.
Okay.
So that will only determine your stability.
Okay. And like next thing is like
Hmm.
it was told like something like about that AP is related to diagonal coefficient.
Oh, yeah. So if this whole thing you cast into a matrix, then
Yeah.
AP would always appear in the diagonal terms.
Okay. So does it make any difference?
It does. So in certain solution methods where you're trying to invert that matrix, if it is not diagonal dominant, then it throws up errors. So it's good to have diagonal dominant matrices where the diagonals are bigger than the other terms.
Okay. So there is maths behind it.
Yeah. Very difficult maths behind it.
Okay. So just what I like
Mm.
have an idea that it must be a diagonal
Yeah,
dependent, something like this.
yeah, yeah.
Okay. And
So the only control you have over there is that certain schemes might give you a diagonal dominant matrix. Then it's a good idea to use that scheme.
what can you repeat?
So let's say you're trying to solve the same problem, let's say by using explicit scheme and Crank-Nicholson scheme. And you see that Crank-Nicholson is giving you a diagonal dominant matrix where the APs are bigger. then it's a good idea to use the Crank-Nicholson scheme.
Okay. Uh,
And
Actually,
this might differ from case to case. I'm not sure.
okay, okay. So I have some couple of doubts,
Hmm.
but can you wait for 2 minutes, like
Sure,
4 minutes,
sure,
please?
sure, sure, sure.
Yeah. I'm really sorry.
Yeah, no problem.
Yeah. Thank you. And so, yeah,
Hmm.
I just want to understand, like, in lecture three, in lecture
Yeah,
three, six.
you can see the screen, right?
Yeah. Okay, it is about that condition only. Okay, that doubt is clear. Diagonal linear calculate after assumption. Diagonals only have to approach of flexity. Okay, yeah. Okay. So about this flux thing,
Hmm. Over here,
physical meaning. Yeah.
over
So
here.
basically, physically, like about any in general, I'm asking,
Hmm.
like about like if I can take any example of, let's say, heat conduction, or that is the most
Hmm.
common example.
Yeah.
So what flux I can physically like visualize, like it is the heat transfer.
Heat transfer, yeah, and it's usually in two modes. So if say the whole bulk fluid was stationary, then also there will be some transfer through conduction. That is what the
Okay.
diffusion term captures that. And if there is flow of particles, that carries the heat, right? Heat energy, whatever. So that is what we call convection in heat transfer. Over here, it is that convection term or advection term. Those two words are used interchangeably.
So diffusion is more a kind of conduction.
Diffusion is conduction is a form of diffusion, you can say.
Okay. And in heat transfer, it was understood like
Mm.
separately. I can understand this
Mm.
diffusion and
Yeah.
convection term.
Mm.
But what about like other things? Like there is a simple fluid flow.
Momentum, right? So
Yeah,
momentum also diffuses, and that's what happens through viscosity. So you'll see in the Navier-Stokes, the diffusion term has uh, the coefficient of viscosity instead of in place of the diffusion coefficient. So that also you can visualize this way that let's say you have a flat plate and you have an expanse of quiet fluid above it. So it's all stationary. And this wall, let's say, suddenly starts moving, which is the, what is it called? The Stokes first problem,
first
right?
stop. Yeah,
Yeah.
I stop first.
So this wall suddenly starts moving. Now, at some point away from the wall, it at t equal to zero, it has no knowledge of this wall moving or anything. Now, the movement of this wall would affect the first layer of, fluid molecules attached to that wall. So they will also move with the same velocity. There will be another layer above it due to viscosity between the layers that will start moving after some time, then the next layer, then the next layer. So in this way, momentum of the wall slowly diffuses above. And one point that was, above the wall, after some time it experiences that the momentum has changed. So that's exactly equal to heat diffusing slowly with time, or some species diffusing slowly with time.
And if this complete volume start moving,
Hmm.
then it is convection, like analogically
Yeah, you can say. Yeah. Yeah, that the whole thing is
start moving.
get some motion. Yeah.
Yeah, actually I forgot, but I have like read about this thing, this
Mm.
momentum diffusivity and versus
Mm.
something that
Mm.
also some kind of diffusivity or something.
Mm.
So like in the fluid itself, like one thing is like because as you discussed, like momentum getting diffused, and
Yeah.
there is one another term
Mm.
I forgot that thing that it is long before. So
Okay.
that also kind of changes. So like this moment,
Mm.
okay, okay. Mhm.
Are you thinking about the Prandtl number, which is the ratio of momentum diffusivity and thermal diffusivity?
Ah, yeah. Okay,
Mm.
okay, yes. You guessed it very right.
Yeah.
It is about thermal diffusivity and momentum diffusivity.
Yeah.
Yeah.
So that
So,
Prandtl number ratio tells you whether momentum will diffuse faster or heat will diffuse faster.
so when momentum diffuses, it will only transfer this, like it will increase the speed or
Mm.
like randomness or whatever I can say.
Yeah. Yeah.
And thermal diffusivity will change the temperature.
Yeah.
Okay. Yeah. Okay. So thermal and momentum. Okay. Yeah, now it is clear. So diffusion and convection terms are that's why I include like in general we have both this thermal and diffusion
Mm.
term.
Yeah.
So it is because of this uh, diffusion captures this thing momentum or
Mm.
like concentration changes or
Mm-hmm.
something,
Yeah.
and this convection term is like this.
Yeah.
Okay, okay. So just a minute because I have some
Sure.
like basic doubt.
Yeah, yeah, take your time. No issues.
Convection is this. Okay, it is convection and diffusion,
Mm. Those are the
right?
two things.
Yeah, just two things, and one is
Mm.
temporal term, like that we
Mm. That's just
collected
what you're trying to solve for. That, at one point,
mostly,
how does it change?
and one source term.
Mm.
Okay, so diffuse. Now it is like yeah, yeah, and like in diffuse in heat conduction problem, we said
Mm.
that that alpha value, thermal
Mhm.
diffusivity,
Mhm.
is like this diffusion constant here,
Mhm. Mhm.
gamma we have taken.
Gamma, yeah.
Yeah, but thermal diffusivity, I think it only captures the thermal diffusion
Yeah. What else?
because it is k by rho
Mhm.
cp. So
Mhm.
like
So
k is
it's like,
conduction
yeah,
and rho cp is
specific heat. So it basically tells you how much temperature will change. K, the conductivity, that will tell you how much heat will flow. But
yeah.
alpha really captures what is the, kinetics of time instead of the dynamics of it. So let's say K was same between two materials, but one material had a very high rho Cp. In that case, alpha would be very small, and for materials with high rho Cp, their temperatures will also not change much. They will only change a little bit, even with the same heat flux.
Yeah,
So alpha tells you how much the temperature will change,
okay.
right? So
But rho
similar to,
cp is
hmm,
like a specific heat.
yeah,
Cp is a specific heat, and rho
hmm,
is the density.
yeah.
So if I multiply density by a specific heat,
Okay,
what
these
this
are
quantities?
these are class 11 questions. You'll have to go back. But see, the main thing is uh, rho Cp into volume of it. That gives you the specific heat of the whole thing, whole mass or whole block, whatever. So that tells you that how many joules of energy is required, how many joules of heat energy is required to increase the temperature by 1 degree C or 1 Kelvin, whatever. So now, if you go to per unit mass sense or per unit volume sense, which is done in CFD or this entire field, where we are looking at control volumes and we are talking about what happens per unit volume. Then instead of rho CPV, you go to rho CP only. That per unit volume, this much energy is required to change its temperature by 1 Kelvin.
No, that's not unlike that. I understand.
Hmm.
Actually, these ratio is yeah, I get it. Actually, this is yeah, I had this thing. It represent a thermophysical property. I have wrote it
Hmm.
like what it is in my notes. Like it
Hmm.
is like K is related to transport property,
Hmm.
and this rho Cp will give thermodynamic property, which is heat capacity MCP. So like it is more kind of how much is stored. Rho
Yeah,
Cp is giving how much is stored
yeah,
versus K is giving how much is conducted.
yeah.
Okay, so yeah, so rho Cp is actually more about storing of energy in
Hmm.
the
Yeah,
volume,
yeah.
and that K is giving us the transport property, which is
Hmm.
like thermal conductivity. But when I go for diffusion,
Hmm.
then I say it is same as thermal diffusivity, but it is not only capturing the how much is transferred, it is also taking a ratio of how much is getting stored.
Hmm.
So that's why like how can alpha be same as diffusion? Because it's not
Yeah,
only capturing the diffusion, it is also taking care of like how much is stored versus how much is getting stored.
yeah. So how much got transferred, that is K, divided by how much got stored, will give me how much temperature changed, right? And that's what we are worried about in these equations.
In general, let's say in
Mm,
general I don't care, like in general case, let's say we
mm,
don't have the thermal alpha. In
mhm,
general, I have like say something is getting diffused, momentum diffusivity or something, then
mm.
I don't take care of how much is getting stored. I only see how much is getting transferred.
No, then also we take care of how much is getting stored. Let's say in the Navier-Stokes equations, there if you're trying to really find an analog with the general transport equation, then the diffusion coefficient over there is the kinematic viscosity, nu, not the dynamic viscosity, mu. So you divide it by rho, and that gives you, how much momentum
Yeah,
energy
yes,
per
yes,
unit
yes.
mass is required.
Very nice. Yeah,
Mm,
yeah, yeah. Very, very good. Yes, we have taken their kinematic viscosity, not
mm,
dynamic one.
yeah.
Okay, so diffusion is more of like taking the ratio of both things.
Mhm.
Okay, okay, okay. So
So,
diffusion convection.
see, the
Yeah.
main common philosophy is that due to transport of something, how much did some other variable change? So, due to transport of heat energy, temperature changed. How much is that?
Okay,
That's the main
yeah. So
question.
that depends upon how much is stored and how much is
Yeah.
transferred. Yes. Yeah. Okay. So basic idea is how much is getting changed.
So, in momentum equation also, due to some pressure or some force, how much momentum changed or how much velocity changed? So, then also you
Okay.
need rho as well, not just mu.
Okay.
Okay.
Yeah, in FDM, discretize it was told that
Hmm.
one problem in FDM,
Hmm.
it is told in lecture that the discretization may not be conservative.
Okay.
So what does discretization may not be conservative?
Okay.
That is about that flux is getting
Yeah, yeah.
cancelled or
This conservative thing we will discuss later. I think one of the lectures later on discusses the
okay.
equations in conservative and non-conservative form. But
Okay. Now
I'll give you the brief idea. So let's say you discretize some equation
not
using FDM.
don't give me
Okay.
the idea. We will discuss it in full fledged form. We will
Okay.
discuss it.
Okay. Okay.
Yeah, so right now, like my question is more of a maths thing.
Mm-hmm.
Like anyway, it is maths, but it's like basic mathematics.
Mm-hmm.
Like I have gone in a little kind of detail about this volume integral to surface integral thing
Yeah.
in vector form. So
Right. Right. Yeah.
even in arbitrary shapes, what
Mm-hmm.
we have taken, like at every small area we consider, we take a normal vector
Mm-hmm.
like direction cosines or something. I don't exactly
Yeah.
remember right now, but
Mm-hmm.
direction cosine in that something, and we
Mm-hmm.
multiply that quantity
Mm-hmm.
and integrate over the surface,
Yeah.
even if it is random or something.
Mm-hmm.
And that change is actually giving us what it is inside the volume. That's why
Yeah.
we convert it from there to there.
Yeah.
That I understand
Mm-hmm.
philosophically,
Mm-hmm.
but more but the thing is like
Mm-hmm.
it's still difficult for me to get the basic idea about what is physically gradient and divergence means, because divergence I think that I found out something like
Yeah.
it is getting how that quantity is diverging from the area,
Yeah.
something like this. But
Yeah.
if you have some better idea about
Mm-hmm.
how this gradient and divergence physically means.
Mm-hmm. So, fluid mechanics is the perfect way to discuss these things. So, when we learn these back in plus two, we don't really learn fluid mechanics much. So, we just learn them as vectors and calculus of vectors. But fluid mechanics is really the way to visualize it. So, divergence. So, if you remember, um, incompressible flows are divergence-free flows, whereas compressible flows may have divergence. So the main uh, logic there is that given a certain control volume or given a certain field, if it's divergence-free, that means around one point, if I draw a control volume, then whatever comes in goes out. There is no difference between the two. Nothing gets
Okay.
stored or depleted. That's what happens in incompressible flows. The continuity equation, whatever u comes in, u into a or u1 a1 equal to u2 a2 in 1D.
Yeah.
That whatever
Yeah.
mass came in, the same mass went out. So that's
Okay.
the idea of divergence. Now, if divergence was positive, let's say you had a source flow. In
Yeah.
potential flows, we learned source flows that, I have, let's say, one pipe, and from that pipe is not part of my control volume, and that pipe is the outlet of that pipe is within a certain control volume. So there is a source of some water coming in, and there is water going out through the whole. control surface. So that will have a positive divergence,
Yeah,
right? So
but it is more.
divergence,
Yeah, yeah, yeah.
yeah,
Please.
yeah. So divergence basically means what is coming out of, one small control volume around a certain point.
It is
That's
just a
a,
quantity. Like it is just a continuity equation.
yeah, it's a quantity. Like it is used in
No, no,
fluid.
continuity. Sorry, like it
Yeah.
is just a continuity. Like just continuity. We are mass in minus mass out. So
Mhm.
that is the divergence.
Yeah. Dou u dou x plus dou v dou y, that is basically divergence of u.
No, when I am saying divergence of u, let's
Hmm.
say it is a velocity.
Hmm.
Does it mean like change in velocity?
No. It means this thing that how much is coming out of one point. Divergence of velocity at one point means how much flow is coming out of that point.
Okay, that how much flow is coming out.
Yeah.
Uh,
So in incompressible flows, it's zero everywhere. Now divergence is used in other things like magnetism and all that. So there also the idea is that, if some field, some electric field is coming out of one charged particle, then the divergence of it will give me idea of something like how strong is that charge or something.
and gradient.
Okay, at gradient, one good way to visualize gradient would be, let's say you're walking over a hilly area. Then, if your gradient is negative, that means you're going down any slope. If you're coming down a hill, then that's negative gradient. And if you're going up, that's positive gradient. Now, how does that uh, translate into fluid mechanics? Let's say you have a pressure field, some pressure distribution around a 2D space. So there, gradient of pressure would be, wherever you're going from a point of high pressure to low pressure, you're going down the gradient. You're following the negative gradient of pressure.
Yeah, and it was told that sometimes we don't take dot or cross product, we just simply multiply. How does it is different from
What? What? Sorry, I couldn't follow.
like sometimes we take dot product that is
Hmm.
gradient or something.
Hmm.
Sometimes we take like we are simply
Oh,
multiplying.
okay. So that depends on the operation and the variable you're operating on. So divergence operates only on vectors. You cannot have divergence of scalars. Whereas gradients operate on scalars. That is simply you can visualize this way that gradient of P and other scalars, gradient of T, the temperature gradient as well. And curl, of course, that acts on vectors only. Gradients of vectors can also be taken, but that's a bit more complicated, where you take gradients of each component of a vector separately.
Okay, but like
Mm.
in divergence, like say simply if some flow is happening,
Mm.
constant velocity, let's say
Yeah.
constant velocity everywhere.
Mhm. Mm.
Now their divergence is zero because but something is emerging.
No, if you have a constant flow field, let's say U everywhere in space,
Yeah.
then you take one point, any random point. Whatever U is coming in, the same U is going out. There is nothing coming out of it, net total.
Okay.
Right?
Yeah. So it is more like capturing a source term.
Exactly.
Okay.
Expansion, basically. In If you read up a little bit on compressible flows, then wherever expansion happens, there the divergence is positive.
Yeah, yeah. It was also in sync. It is negative, and
Mm.
sources it is
Mm.
positive, something like this. Yeah. So I will look more into it, and then like also one thing like out
Yeah.
of this thing, like uh, like if it is not a problem, then
Mm.
if I can have some contact of you so that
Of
I
me?
can
Okay, I'll share my email ID with you in the chat box.
yeah Like or you we have discussed here discretization of all those equation, but we have not discussed about like how they are
How there?
derived
Which equations?
all these equations.
These diffusion equations,
Yeah,
the ones
diffusion
over
and
here.
all those things.
So
Yeah,
those were done earlier, no, in the
yes,
initial
you.
few lectures. So
I
this
think it
is
is just a minute. It is G. Okay, it is wrongly written.
so if you
No,
remember
you're.
the general transport equation, this is just a short of that, some simplification of that.
Yeah, that I will see, and that's what I'm like. If I might get any doubt in that,
Sure,
then like I can ask, like,
sure.
uh, like through this email ID. Yeah.
Yeah,
Okay. It is Gmail, right? Not Smail.
it's Smail.
It's Smail.
Yeah, it's my student email ID from IIT Madras.
Okay. Okay.
I think it is correct. You don't have to change anything. You can send anything here.
I
I'll get
already
it.
changed it.
Yeah,
But it's generally, I think it has like right now it has changed, but earlier it was Gmail only, right?
maybe.
Okay. Yeah. So, okay. Okay. So, like, I will not bother you too much, but if it is really a doubt, then only I
Sure,
ask.
feel free to. Yeah.
Yeah, and diffusion. There's yeah in coastal. Okay, okay, that's I understood. Okay, so yeah, one more thing. Like you told about like last in the last session, there is no
Mm.
not much time about like you really brought me the interest. Like we can have different fields of application for CFD.
Oh, yeah.
Yeah. So, but you said that it is the same equation we are applying at different fields.
Hmm.
So, because like if we only discussed about this math thing, then it look more like of same thing or like a little that thing. But the application part is different than that. Like how
Yeah, applications keep changing. But what I meant to say is that the main uh, skills, those remain the same. If you learn about, let's say you're learning this thing that explicit schemes are conditionally stable and not unconditionally stable. You can carry this on, this knowledge, you can carry this on to different equations. They don't have to be related to fluid mechanics at all. Let's say you're doing some, you know, electromagnetics. You have some partial differential equations and you're trying to solve them. Then also this idea of explicit schemes being conditionally stable will translate.
okay. And you also told about like you're like doing maybe internship in GE aerospace.
Yeah.
Yeah. So like here, there, like how is the application like part?
There are
How they are
different
applying it?
there are different things. So, in order to make an aeroplane fly, you need to know the aerodynamics of the uh, aeroplane in question. Then combustion goes on in the aeroplane engines. That's
No, that
also
is very
basically a
general. Yeah, but what I'm asking like how
mm,
industries are using CFDs, like how what is this simple
mm,
application what we are discussing here?
mm.
That's the same thing which are applying
Yeah,
getting applied to.
yeah. It's bread and butter for a lot of people.
Okay, okay.
Mm,
Yeah, actually, let me tell you one thing. Like I
mm,
have multiple time I have
mm.
actually. What should I tell? It's just a personal thing.
Okay, so I can stop recording if you're sharing personal
Yeah,
things. Okay.
yeah.
Yeah.